Hello, Washington Liberty chemistry students. This is your Unit 2 lesson on experimental design. This is hopefully a review of terms that you have heard in previous science courses. So first, a few definitions. When you are designing an experiment, you need to have these four things. An independent variable, sometimes called the manipulated variable. That's the variable that you change. A dependent variable, sometimes called the responding variable. That's the variable you observe or measure. Constants, and these are actually variables, but you keep them constant so that you can see the effect of the independent variable on the dependent variable. And then the control is the IV group, the independent variable group that is the no treatment or the normal treatment group. It is often used as a comparison. So let's just go through an example. Suppose you were growing plants, and here you have two sets of plants that you have been growing, one treated and one not treated. So here's your first problem. What is the effect of different concentrations of fertilizer on the height and health of those plants? So that was your problem, that was your experiment. Can you, within that experiment, identify the independent variable, the dependent variable, important constants, and what the control might be? If you did this correctly, you would have said that the independent variable would be the concentrations of fertilizer, so your different concentrations of fertilizer. Your dependent variable, and oftentimes you'll have more than one dependent variable, especially with a plant project. Height is not always a good indication of the healthiness of the plant. So height and health would be a more qualitative dependent variable. Now constants, this would be important things to keep the same so that you could really see the effect of the fertilizer. So like the amount of water, the amount of light, the type of seed, the type of soil, those would all be important constants. And the control group would be the group that was not given the fertilizer, because that's the zero group or the normal group. You have to actually add fertilizer. Most plants don't get that, so that's your normal group. So just a little bit of science. We're going to look at this particular situation of why do apples turn brown, learn a little bit about it, and also identify and talk about the parts of experimental design.
Let's say you've got an apple, and it looks delicious, and then you bite into it, and you find out it's all gross and brown inside. Or maybe you just want to eat half an apple, so you slice it and leave the other half on the counter. An hour later, it's a brown, mealy mess. All I wanted was an apple, and now all I have is a mouthful of disappointment. What happened? Well, different kinds of cells have different kinds of enzymes, and one enzyme that's found in the flesh of fruit, as well as the flesh of people, is polyphenol oxidase, or PPO. Its job is to interact with phenols, simple organic chemical compounds that can be found in pretty much everything alive. Specifically, PPO oxidizes these phenols wherever it can. That just means that it encourages them to bond with oxygen atoms, and it'll do this as long as it has access to both phenols and oxygen. Now, the oxidation of phenols kicks off a long and complicated chain reaction that ends in a protein you've probably heard of. Melanin. The same pigment that controls your hair and skin color is also produced by fruits and veggies. It's what you're seeing when your apple turns brown. And actually, melanins are a lot more widespread in plant tissue than in our own tissue. We can only really produce them in our hair, eyes, and in the bottom layer of our skin, whereas plants have them practically everywhere. And the melanin that plants make serves a different purpose. So when plant cells are damaged, melanin is produced to surround and slow down any possible infection. That is why, if you've ever cut open a rotten apple, the rotten spot is usually surrounded by brown flesh. It's essentially the apple's immune response to rot. Unfortunately for us, it's also the apple's response to any kind of damage. You drop the apple on the floor, it kills some apple cells and starts cranking out melanin to protect itself. And when you cut an apple into slices and serve them with crackers and cheese, those slices are going to brown really, really fast. Because not only are those cells damaged, but they've been exposed to air, which, as you may have noticed, is full of oxygen, which allows the PPO in those cells to basically throw a big oxidation party. It'll oxidize all the phenols. That apple is going to be so safe. Except it's not going to be safe at all. You're either going to eat it, or you're going to throw it away when it gets all brown and nasty. Because those nice fresh phenols are really tasty, but the melanin, not so much. But on the bright side, the brown color in cocoa, raisins, coffee, and tea are all caused by this exact same oxidation reaction, and that actually gives those things the taste we like about them. Thanks for watching this quick question, especially to our
All right, so here's your second problem. A student is studying the effect of several solutions on the prevention of browning of apples. The student used solutions having different pH values and immersed 3 apple slices in equal volumes of each solution. He then timed to see how long it would take until the apples showed browning. So reading this problem, what is his independent variable, dependent variable, constants, and controls? Jot them down and let's see if you're correct. So the independent variable was the pH because he was using different pH solutions. The dependent variable, the one he was measuring, was the time to brown in seconds. And the constants would be things like the volume of the solution, the type of apple, the size of the slice. Those would all be important. The control possibly would be the apple soaked in neutral solution because that's sort of the normal pH. Or you might just compare it to an apple not soaked at all. Those would both be possible controls. Now, let's talk about hypothesis. Hypothesis is a reasoned prediction of the outcome of an experiment. And can you make a prediction about the browning of the apples after watching the video in terms of what do you think the acid might do to the browning of the apples? See if you can write one. Now, a hypothesis usually has a format of if, then, because. So, if the apples are immersed in different pHs, then what do you think will happen and why? So here's mine. If an apple is soaked in more acidic pH solution, then it will brown at a slower rate because the lower pH inhibits the reaction with PPO, which is the cause of browning. Now I chose, because I knew a little chemistry, to say, oh, it's going to inhibit the reaction. You might have said, because there was no background, that maybe it would speed it up. But you should have an if, then, and because statement. So if an apple is soaked in more acidic pH solution, that's our independent variable, then it will brown at a slower rate, and that's our dependent variable, because the lower pH inhibits the reaction with PPO, which is the cause of browning. So you always have a because. So it's not just a guess. Now a little bit more experimental design terms. We do repeated trials in all of our experiments, and repeated trials are done to verify the validity of the experimental method. A good experimental method will have good repeatability. And scientific data is organized in data tables and graphs, because graph data gives us a picture of a relationship between independent and dependent variables. Now, to graph data, the following standards usually apply. When you're graphing data, you put your independent variable on the horizontal axis, and you put your dependent variable on the vertical axis. Scales and units are proportional. You don't go 1, 100, 120. You proportion them out so that the difference between 1 and 10 and 10 and 19 are the same. Regression lines, best fit curves or lines, are used to determine the relationships between variables. Is it a direct relationship? Is it an inverse relationship? Now, to remember the conventions for doing a graph, you can use this acronym, DRY mix. So dependent variable or responding variable goes on the y-axis, the vertical or y-axis. Manipulated variable or independent variable goes on the x-axis. So, for example, as you can see this visually, the independent variable goes on the x-axis, the dependent variable goes on the y-axis. We can actually graph data and look for linear relationships. You can even do a line of best fit. Never forget to always give your graph a title. You can see also that the scale here is proportional. There's just as much room between 0 and 5, and 5 and 10, and 10 and 15. So let's look at this one. Can you just identify by looking at the graph what the IV and the DV would be in this experiment? See if you can. And see if you can formulate a question that would be the question that this graph was answering. So the IV is on the x-axis, so that's time, and the DV is on the y-axis, and that's speed. So this looks like an acceleration graph, but what is the effect of time on speed? So it looks like as the time increases, so does the speed. And that is your lesson. Thank you.